This is a part of the Conservation Lecture Series. You can view the schedule and register for upcoming lectures, watch videos of past lectures, and subscribe to our mailing list. The web address to our Conservation Lecture Series is listed or identified here, and as well as Margaret Manter's email address. To subscribe to lectures is on the internet page. You just subscribe here, and this is where you would find past lectures and some upcoming lectures. So the lecture schedule upcoming, here's a list of some, and I know that there's some even going into November and December. We're starting to add some restoration lectures. 2 of them identified here, and I know that there's 2 more that are in the pipeline as well. Some pretty interesting talks. For today's lecture, I asked the audience members to hold all questions until the end so I can pass around, or we can pass around the microphone, and the people listening on the webcast can hear the questions. For those of you participating via webcast, you can type your questions into the chat box, and I'll read the questions for the presenter at the end of his presentation. We'd like to thank Trevor Porter, who's in our audience from our North Central region, for organizing today's lecture. Today we are pleased to have Dr. Joshua Veers presenting a lecture on process-based restoration of the Central Valley floodplains for multiple social ecological benefits. Dr. Veers is an associate professor and watershed scientist at UC Merced in the School of Engineering. He received his PhD in ecology from UC Davis in 2003. After completing his BS in International Agricultural Development in 1994 at UC Davis. He is the UC Merced Director of the Center for Information Technology in the Interests of Society and the co-director of the newly formed UC Water Security and Sustainability Research Institute. He was recently named to the Public Policy Institute of California's Water Quality Center as a research expert in the field of watershed scientist. His research interests and projects investigate the geospatial aspects of watershed science with a specific focus on the watersheds of the North Coast, Central Valley, and the Sierra Nevada. His watershed research activities include aspects of natural flow regimes, climate change, water management, land use, sustainable viticulture, freshwater ecosystem conservation, and riparian restoration. Please welcome Dr. Veers.
Thank you. Thank you for having me, and probably enough about me and more about what I do with my colleagues. We're going to close the window here, I think. Great, and hello to everybody on the internet today. Good afternoon. Before I get started, I really needed to point out that I'm benefiting from the hard work of many, many other people. And everything I'll show today is really based on their efforts. I've been fortunate to be a part of this research for over a decade at this point, and I certainly wouldn't have been able to do it on my own. They're at the University of California, Davis, and the Center for Watershed Sciences. There are also colleagues at Washington State, at the South Yuba River Citizens League, colleagues at the Nature Conservancy, Point Blue Conservation Science, and elsewhere. This is really a team effort. Hopefully the work shows that. I'll get to the Black Swan and the Brown River in a bit, but before we do get there, I want to be able to point out that I am from the University of California, just a different campus. UC Merced is the 10th and newest campus of the University of California system. Opening its doors in 2005, we went from 600 students to over 6,000 students today, and we anticipate getting to 10,000 students by 2020. So we'll double our physical footprint and double our faculty in that time, creating an identity for ourselves in the San Joaquin Valley and in STEM field, science, technology, and math. If you've ever been to the UC Merced campus, it does look like this. There are a bunch of dairy cows. There are also a bunch of vernal pools. We're fortunate to have 7,000-acre natural reserve adjacent to campus that we use for teaching and research purposes. And we're also fortunate in being a new campus. All of our buildings are brand new. 14 of those buildings are Platinum LEED certified, one other's Gold certified. So we take sustainability very seriously. Now moving on to California water. I usually show this to my colleagues in other states and indeed colleagues in other parts of the world and say that this really summarizes where we're at with California water issues. And if you think about it, it is a vast engineering work delivering water to a common pool resource with a lot of consumers, 38 million consumers, and how we go about moving that water and enjoying it for a variety of purposes is kind of central to what we've been experiencing the last few years. So it's all fun and games until the water disappears. I'm going to touch briefly on some of the insights that we've learned that might help us actually weather storms such as this, in part because we expect that changing hydroclimatic conditions in the coming decades will challenge the very infrastructure that we've built. And my belief and experience that some of the things that we can do today will certainly help better prepare us for tomorrow. As you know, the Sacramento-San Joaquin Delta is also a series of tubes that deliver water to consumers downstream, in this case canals and delta waterways. And the very nature of the questions that we try to answer with our research are in part to help solve some of the puzzles, if you will, that are present in the Delta. As you know, about 48% of California drains out through the Sacramento-San Joaquin Delta, creating the largest estuary on the western United States, creating a mosaic of habitats and waterways. But it's very different today than it was in the past. And in fact, what was a flux of water moving in and out of the Delta based on a Mediterranean system that in some years would be quite wet, in other years quite dry, and an annual drought that we call summer, that the flux of that water created a vast network of habitats throughout the region. That's obviously changed now, in part because of the way we've managed that water, more of the water moving through aqueducts and exported out of the Delta, and what remains being used for salinity targets and some species-based targets. Looking at the Delta as a hub, it's important to recognize that the infrastructure in and around that isn't just the water itself, but it includes a myriad of transportation networks. It includes pipelines, it includes railways, and it's the centerpiece of an engineering work that delivers water to 38 million people. It's also highly fragile. The trends in outflows have always been declining regardless of the type of water year there's been, at least since the 1980s. For the dry and critically dry years, it's been even more severely diminished. It's created a modern mosaic of habitats that are highly simplified compared to historical conditions, with the loss of ponds, lakes, channels, and flooded islands. I'll talk a bit more about that as we move forward. It's also seen the decline of California's native fishes. Most notably, salmon runs throughout the state have lost access to spawning grounds. Changes in flow regime have also further exacerbated their persistence. But it isn't just salmon. There have been a decline of all of California's native fishes, going from 44 reasonably secure species in 1989 to 22 in 2012, and the number of listed species increased. It's no small wonder that given the amount of dams created in California that the ecosystems downstream have suffered disproportionately. The sensitive taxa highlighted in red here show that most of the Sacramento and the San Joaquin Delta, as well as the Klamath Basin, have been severely affected. The pelagic fish declines within the Delta proper are well documented and something many of you are probably aware of. This is further exacerbated by subsidence within the deltas. And to underscore this problem, I like to characterize it to my students as if you were taking a giant mixing bowl and you were pushing it into a bathtub full of water. The further you push it in, the more difficult it is to push, and then ultimately it tops over the edge and fills the bowl with water. Our delta islands are very similar to this, in that the oxidation of the exposed peat soils and the volatilization has reduced the amount of soil in those islands, and many of those are now below sea level, in some cases more than 15 feet. When you add sea level rise to this, and perhaps a big flood, the exponential hydrostatic forces on those levees, of course, create pressures that are perhaps not withstood, in part because many of these levees are poorly engineered. It's a recipe for disaster, perhaps, or at least failure. And we'll talk more about failure going forward. Much of what I've talked about is something that has been in the making for a long period of time, and in fact, coming westward, European Americans settling California following the gold rush of 1849 have transformed California's landscapes and riverscapes to such a degree that they're hardly recognizable. There are only a few places left in the state that we can use as benchmarks, if you will, for what we might want to attain, and certainly as indicators of what has been lost. Going through the hydraulic era and the building of this vast engineering works came to a close in the 1980s for the most part, and since then there have been a number of policy decisions that have been made trying to figure out next. Many of those are quite contentious still to this day. It's my hope that going forward, particularly with the passage of Prop 1 and the groundwater regulatory reform, that we're in a new era. That is yet to be determined. From all of this work, there are some lessons learned, and I'm going to go ahead and give you the punchline now, in part to think about as we go through the rest of the talk. These have to do with restoration, resilience, and reconciliation. When we talk about restoration, we're talking about reconnecting land and water to rebuild ecosystem functions. We want to support ecosystems within the context of continued human use and restore natural processes where possible. We need to use management tools, infrastructure included, and technology where needed in order to accomplish this. Resilience. We're talking about coupled human environmental systems where we maintain the structure and function despite disturbances. We are expecting a system of change with natural or desirable multi-states, and we need to build adaptive capacity or flexibility within these ecosystems, and also social systems to learn to respond to these disturbances. It will require landscape redesign, incorporating natural and engineered infrastructure to create a biologically diverse and resilient landscape. But we need to be able to support both agriculture and natural ecosystems while reducing the impacts of climate change. This is a tall charge. I believe that reconnecting floodplains is a no-regrets policy with multiple benefits. These setback levees can improve water supply, they can improve water quality, they provide recreational benefits, agricultural benefits, and ecosystem benefits. I'll focus on the ecosystem benefits for the remainder of the talk. When we talk about reconciliation, ultimately we're saying that multiple benefits are possible, but adaptive management is required and novel ecosystems are likely. We won't have time to get into novel ecosystems, but we will talk a bit about these multiple benefits. These multiple benefits include flood storage and attenuation, groundwater recharge, creation and maintenance of fish habitat, the maintenance of agriculture, waterfowl and shorebird habitat, as well as the recreation. In particular, the work that we've been doing has focused on the flood storage and attenuation aspect, as well as creating fish habitat and opportunities for local groundwater recharge. Adaptive management is required. Knowing how to do it is challenging. It requires that science informs decision making and that we use experimental ecosystems that are small enough to be manageable and large enough to be meaningful. And I believe our work at the Cosumnes River, in fact, meets those criteria. This is the photo that has changed how we manage floodplains in California, and I'm going to spend a bit of time telling the story behind it. The Cosumnes River is a scientific proving ground. As early as the late 1980s, the Nature Conservancy and state and federal agencies, the Bureau of Land Management, then the Department of Fish and Game, was working to secure habitats along the Cosumnes River. It was funded in part by what was then CalFed, and a number of foundations stepped forward, and the Center for Watershed Sciences at UC Davis started working in the area in the late 1990s. We've been fortunate to receive funding from a variety of sources over the past 2 decades to carry out this work. And the results from that include a lot of papers in academia, which does us well, but it also includes insights that are used in management throughout the region, which does everyone else. I'll be talking a little bit about what we call the Black Swan. For those of you who are familiar with it, Hassim Taleb published a book called The Black Swan that characterized this phenomenon of things that were completely unforeseen but totally predictable. And it marks the time when natural historians were exploring the world, and at the time they thought there were only white swans. And then they got to Australia, and there was a black swan. It was because they didn't see it coming, but in retrospect it was completely predictable that there would have been one. This has now been applied to things like financial markets and engineering of bridges and a number of other things where we can anticipate in a predictive sense that there might be failure within the system, but when the failure happens it's completely unforeseen. So we'll be talking about the black swan and these brown rivers and the insights that come from flooded landscapes. Thinking about what the delta and its periphery looked like back in time is somewhat hard, in part because the evidence for that has been missing. We didn't have the visuals, we didn't have the data, so to speak, in order to reconstruct that landscape. As it turns out, it was an area of perennially flooded wetlands, and we're just now starting to understand what that means. But to frame this a little bit more acutely within the context of how ecological systems develop, is that there are often these feedbacks where we go from a period of equilibrium, and then for whatever reason there's dissolution and we have to reorganize, and there's a period of growth, and then a period of stasis. And so you can think of that period of equilibrium and the dissolution that happens with that as perhaps one of these black swan events. Similarly, when we look at the literature around the science of rivers and watersheds, we can see that there were some breakthrough moments, things that we should have seen coming, that were perfectly predictable given the nature of data, but it wasn't until something happened that it was easy for us to see. So these papers now are largely around the natural flow regime. Poff et al. In 1997 had a seminal paper describing the way that flows work in nature. The natural flow regime being able to characterize the magnitude, the timing, the duration, the frequency and rate of change of river flows was pretty instrumental in thinking about riverine ecology. And similarly, Roskin, many of you are familiar with, began to type the physical nature of river systems and how they responded. Strangely, these two schools of thought have been running independent of each other and are now just now coming together for the insights to inform each other. We believe that the work that we've been doing on the Cosumnes, in fact, embodies both of these things. So again, in the late 1800s, there was a vast network of very complex habitats. Today, highly simplified and also highly managed. How do we make sense of it all? Well, the hydro modification that happened throughout the delta is fairly predictable. Lots of levees, channelization, dams, and water diversions. Perhaps its impact on the natural flow regime was less predictable. Changes to the magnitude, timing, duration, frequency, rate of change, and the connectivity of rivers to their floodplains. So we had a period of growth and thinking about restoring the landscape, the delta, and the riparian ecosystems that fed it. A lot of that was based on looking at extant natural habitat, oftentimes valley oak riparian forests, that were sparsely distributed throughout the valley. What were the remnants? What was left? And as it turns out, parts of the Cosumnes River had very nice, large, intact riparian forests, in part because the Cosumnes is undammed. It had that natural flow regime. The reason that the Cosumnes largely remained undammed out of the 14 major basins on the west slope of the Sierra Nevada is that it had the lowest yield. It's the ugly duckling. It had the lowest elevation, one of the smallest watershed sizes. The amount of water coming out of the Cosumnes was not worth going at. And it didn't have very good places to build a dam. It was the one that was left over. But because of that and the fact that it floods regularly meant that many of these forests still remained. So an attempt was made to mimic those forests and to plant other forests adjacent to them. And so this horticultural approach to rebuilding a late seral stage forest involved things like planting acorns and putting, and I'm not kidding, prisoners out into the field stomping acorns in the ground, and also having Boy Scouts and Girl Scouts and others. And I think it was a feel-good time, if you will, trying to do something back to nature. And in some cases that worked out. And for quite a while, in the late 1980s, early 1990s, this was the paradigm for which we conducted restoration. It was based on this idea of the chronosequence. Through time, we would build up the ecosystem as measured by biomass or the total number of trees or the canopy or what have you. That changed over time, in part because not all of these restoration activities were in fact successful. If we were to look at this particular restoration site, we certainly have those oak trees, but they're not flourishing, and they don't have the understory. And what I would say is that they're missing the process to create them and sustain them. And it's no surprise then that the literature began to identify some of these things, that riverscape restoration efforts cost a lot of money, in some cases over $1 billion a year across the nation, but only 10% of those projects had any form of assessments or monitoring. And the projects themselves were not designed to evaluate the consequences of restoration activities. Moreover, there was a call for us to actually link science with policy and implementation, and that we needed to accept the complexities and uncertainties in our restoration actions, and that we needed a theoretical framework to be able to generalize across different river systems, and that restoration monitoring was needed at the correct scales of measurement. But this was a period of equilibrium until something happened, and that was the Black Swan event. As Jeff Mount said, failure is always an option. In this case, the failure was a levee. A levee along the Cosumnes River in 1985, it was just a routine failure. And what happened from that, though, was a change in paradigm. The farmer was unable to rebuild the levee, and the sand splay that was created behind it had propagules, and those propagules were cottonwoods. And those cottonwoods began to grow very rapidly. And fairly quickly, it became a forest. And it was at that point that river managers and preserve managers recognized that letting the river do the restoration might be a good way to achieve success, if we just let the river have room to do its thing. So in 1995, there was an engineered levee breach to see if we could recreate the same condition. So that intentional breach became the intentional forest. The accidental forest from that levee failure is shown in the lower left-hand corner. The engineered levee breach resulted in a sand splay with propagules and ultimately a cottonwood forest. What we also recognize is that it wasn't just propagules and sand that came onto the floodplain, but there was an influx of organic and inorganic materials. There were nutrients, there were pumpkins, there were even fish, and that was fascinating for us. It was really a time of a paradigm shift. So working through what was then CalFed and funding associated with that, we began to instrument these floodplains to determine what was actually driving these observations. So through those engineered levee breaches, looking at things like primary productivity and chlorophyll shown in this photo here, we could look at the hydrodynamics to see how that changed over space and time, and ultimately coming up with some recommendations about how floodplain connectivity could drive physical and biological systems. We were fortunate in that most of that time was a wet period, that there were actually lots of floods for us to study. One of those insights was that it was the flood pulse itself that provided most of the benefit. Compared to the riverine productivity shown there on the bottom for the zooplankton and the chlorophyll A, which remains fairly steady, that the flood pulses themselves brought on these spikes, initially in primary productivity, the chlorophyll, then zooplankton, and then ultimately fish. And Carson Jeffries saw this coming and designed a very nice little experiment. So this is the results of his master's thesis work and the photo that changed how we do business. We were able to show that the floodplain raised Chinook salmon that were replicated and nearly genetically identical, given that these were hatchery fish, not only had higher survivorship, so there are more of them, but they grew bigger much faster. And if there's anything we know about salmon, is that the bigger they are at the time of out-migration, the greater the likelihood they'll survive out-migration, the greater the likelihood they'll survive oceanic conditions, and the greater the likelihood that they'll come back to spawn and reproduce. We were giving them a head start on life. The invertebrate productivity flows from that really formed the basis for understanding of how fishes were responding, and beneath that it was the flows of water that were informing how we understood the ecology to work. So then it was a new time for us to look at connectivity and process. So rather than those horticultural restorations and the total number of acres over time, we began to look at process-based restoration. And you could see by the late 1990s, there were a number of acres in the Cosumnes area that were undergoing process-based restoration. So the paradigm had shifted from one of just trying to measure an endpoint outcome to one focusing on processes and fluxes within the environment and recognizing an important thing. Not all years are good for all things. Some years might be good for cottonwood recruitment, other years might be good for salmon. Understanding that it's a mosaic over a large area and over a long period of time required that we think about things a little bit differently. To put it in perspective, however, that accidental forest, which is in the center of the photo, is now surrounded by other forests, including the intentional forests and ash forests that are growing around it. And in fact, if we were to update this today, I know that many of those brown patches, in fact, are green despite the drought because of the forest cover. The other thing that we noticed, however, is that many of those forests were having a hard time being sustained, in part because their access to the local water table was diminished. In fact, the Cosumnes, despite being a free-flowing river, spends a good portion of the year dry. And one of the studies that was associated with our, what we call Cosumnes Research Group 2 set of studies, focused on the groundwater dimensions. Graham Fogg and his student Jan Fleckenstein and others developed a regional groundwater model to show that there were two cones of depression, one under the city of Elk Grove, the other under the city of Galt and some of the surrounding agricultural areas that were effectively dewatering most of the Cosumnes. Some of the insights that came from that, however, was recognizing that we needed to take advantage of different opportunities, such as releases from the Folsom South Canal to pre-wet channels, if in fact we were going to entice salmon to move up early. From this developed a much more complex conceptual diagram of what we thought the Cosumnes was doing. It wasn't just the hydrologic regime or that natural flow regime and the geomorphic nature of that floodplain resulting in primary and secondary productivity and ultimately feeding fish and birds and bats. But the groundwater was also a part of this hydrologic balance equation and was a necessary part of us thinking about process-based restoration. And in general, the question was, how can we actually recharge that local aquifer if in fact we're going to have multiple benefits from this restoration. From that emerged the idea that we could use the Cosumnes as a scientific proving ground using what's called a Bakke experimental design, a before-after control impact study, where the before is the before floodplain reconnection and after is the after floodplain reconnection. The control are all these unrestored parcels surrounding our existing study site, and the impact is being able to evaluate the process of process-based restoration against horticultural restoration. So working with the Nature Conservancy, Point Blue Conservation, and DFW, we were successful in getting ERP funds to extend the study upriver north of Twin Cities Road. We had 7 major components to the biophysical monitoring aspect of this study, including groundwater response, soil carbon development, aquatic ecosystem dynamics, geomorphic responses, and hydrochory. Working with Point Blue, who was focusing on birds, and with the Nature Conservancy focusing on vegetation, we developed a team that would go after this. Little did we know that we were going to be studying floods during a decadal drought. The rest of the story is what we are making the most of a flood study during a drought period. In concept then, it was removing or setting back a levee and being able to see whether in fact these forests and floodplains return to some reference condition. Being able to look at the bird response from that, being able to look at the soil carbon development, how the shallow and deep aquifers responded, how the in-channel water chemistry and fisheries changed as a function of those floodwaters, and ultimately looking at floodplain connectivity and the benefits from process-based restoration. This is over a fairly large area, much bigger than anything we had done previously. It included some DFW lands in the Shaw Forest north of the study site, but the main primary channel there, coded in dark blue, is north of the Twin Cities Road. That's between Galt and Elk Grove. If you've been along I-5 or Highway 99, it's that big patch of forest in the middle. Totaling about 1,000 acres total, this study required mass excavation of levees. This wasn't just an engineered breach. It wasn't just a notch. In many cases, it was a wholesale removal, over 300 feet in one section. Required bulldozers and graders and tractors and trucks and continuous operation for almost a month. The benefit of that is still being untold. So that Black Swan in the Brown River, the failure of that levee gave us insights as to how we could manage these landscapes. The Brown River is what came next. So using this study, we're now seeing how those multiple benefits are received from a levee setback experiment. Perhaps what changed our thinking, too, wasn't just this levee failure, but new information that was being made available. Allison Whipple, a doctoral student at the Center for Watershed Sciences, had written a very nice book while she was with San Francisco Estuary Institute, detailing the historical ecology of the Sacramento-San Joaquin Delta and its estuary. One of the pieces of evidence that came from that book was a map. And that map in 1859 indicated that there was a high water and a large body of water running down the slough. And the map clearly labeled the sink of the Cosumnes. In other words, we were in the process of looking at a river when in fact it had been a distributary river channel and a perennial wetland. It changed our perspective, in part because we were looking at the channel in a place that it didn't used to be. And we were looking at little sloughs that were used as ag ditches that were likely remnant channels previously. And that tule marshes and willow thickets and riparian forests were flooded for weeks to months at a time. We had to change our expectation in some way because this particular restoration was probably not going to recreate the sink of the Cosumnes. But there would be some of these benefits. So historically, we were right at that ecotone, breaking out from upland forest to lowland alluvial, riparian forest, and tule marsh. Much of that had been removed. We had to change our expectations then of what the flow regime was likely to be like, and in fact that the remnant conditions were likely to be compressed over a much shorter gradient. It also meant that the inundated area was likely to be much different than had been previously. And in fact, we would have received much larger flooded area much sooner with lower flows under historical conditions, but because of the hydromodification, in fact, there was a threshold with very little flooded area until we topped over the levee. Now with the levee setback, we could expect greater frequency of flooding. And we wanted to know how this flooding would benefit native fishes, in part because there's so little habitat left for them. So taking that bird's eye view, and during a drought, if you look at the lower portion of this photo, you can see that it's the leading edge of last year's first rain. Being able to take advantage of a flood then became very important as the last few years have been quite dry. And in fact, looking at the frequency for the total number of dry days for the Cosumnes, which is highly unique in part because it has 100 years of daily flow records, we were able to show that the drought, in fact, is somewhat bimodal. The number of consecutive days less than 100 second is often quite few, but sometimes is over 150 to 200 days. The one outlier there, which was almost 600 days in length, was the 1976-1977 drought. We haven't quite recreated that with this drought, but presumably there's still. So looking at the frequency of these floods and thinking about the new floodplain and its restoration opportunity, we began to examine how the water years were playing out as a function of the flood duration and the peak daily flow. So it wasn't just the water year, but it was the flood year. What type of flood year could we expect? Based on the work of Eric Booth and Jeff Mount and others, we've since extended these water year types and flood typologies, if you will, to look at how they are across the last 20 years of our experience. It's no surprise that the water year type 1, which is the driest water year type, where small floods are dominant, has been the most persistent in the last few years, which of course is during the time of our study. But it doesn't mean that there aren't interesting things to study while it's dry. And I'm just going to update you on some preliminary results from those three areas that I mentioned: fisheries response, a geomorphic response, and groundwater response. In this case, you can see from the clipped adipose fin that the steelhead is an errant wanderer, most likely from the McCullum. But this green sturgeon, on the other hand, actually accessed the floodplain and was the first documented usage of a floodplain for the Cosumnes by the species. It's a very interesting system. And in fact, our studies have been able to show something that people have always thought from intuition, but never had the numbers to show, which is that native fish preferentially leave the floodplain when the timing is right. And if you look at the percentage of native fish exiting, it's always during that recession limb and before disconnection. So if you look at where the percentage of native fish is 0, it's all after disconnection. For some reason, the native fish know when to leave, and the non-native fish stick behind, only to become bird food. The ways in which we calculate these numbers include pike netting, which we set up in stream, as you can see here. So this is a riverine sample versus a floodplain sample. This is a drainage swale coming off of the Oneto Denier property. And this is another look at it during flood stage. All kinds of native species were found on the floodplain, including the Sacramento blackfish and the split tail. There are also a lot of non-native species that are found on the floodplain, including this carp. This was the largest fish that was caught this year. There were also a few spawners. Unfortunately, there were not many, as there was only really one opportunity to move upriver. In terms of the par that were out migrating, there were only 2 that were caught in our pike nets. But that event did provide us with the opportunity to document floodplain processes. And I'm just going to show a short video of that mid-February storm to give you a sense of what these brown waters really look like. So they're rich in sediments, they're rich in nutrients, and they provide the process by which to reorganize floodplains. So looking south towards Twin Cities Road and then turning back north upriver, you can see that the large excavation area there is fully inundated, as are these agricultural fields that were previously under production. Taking that bird's eye view, we can use new technologies to document these floodplain processes. LIDAR, or light detection and ranging in particular, can be used effectively to be able to quantify changes on the ground. We also use unmanned aerial vehicles or drones in order to do some of this work, as well as LIDAR mounted on small utility vehicles. Here, this will give you some sense as to the amount of data collected as we use the mobile LIDAR to scan that excavation site. It's collecting about 70,000 measurements per second as we drive around. It's no small piece of data. but it does provide us with highly accurate, within 1 centimeter, elevations that we can then use to gauge the total amount of sediment either moving onto or off of the floodplain. These new technologies provide us with things that we didn't have 10 to 15, 20 years ago, and the resolution necessary to quantify to very minute scales as to what the geomorphic change and the process is associated with that across the swale and the excavation site. So looking at this year's data, we can show that it's a highly variable floodplain with different inundation thresholds. So at the top of the map is the primary excavation, which floods at about 2,000 cubic feet per second. There's a secondary accidental breach at the elbow there, which floods at 1,800 cubic feet per second. But the drainage swale itself is a bit of a backwater, flooding at 300 cubic feet per second and staying persistently wet for much of the year. Looking at the timing and duration of those floods, you can see that the swale downstream remains connected for the longest and has some of the deepest water depths. Whereas up at the top, it doesn't stay nearly as connected as long. This has important implications for the ecology, but also the saturation of the Vado zone. This second flood here in February showed some similar patterns in that gradient from the north to the south. Perhaps what was most surprising to us wasn't just the deposition of these materials, largely snags and logs and sticks, and it wasn't the crevasse splay with the sands, and it wasn't the scour that was digging along the riverbanks, but in fact it was the deposition of sediments within the channel that proved most striking. So within the channel itself we had over 1 meter of deposition, and it consisted of sands and gravels. Not many cobbles in the system, but it completely covered what was bedrock. The Cosumnes had been suffering from incision for quite a few years, but this particular levee setback and excavation reduced the stream power, and those drops in velocities associated with that dropped out the suspended embed load within the channel itself. And so meter of aggradation in the system, and sorting of these sediments and the creation of sinuosity within the channel. This was completely unexpected. Using real-time kinematic survey data, LIDAR, and other sources, we were able to calculate to very high precision within 2 centimeters in elevation what the differences were between the pre and the post, so the before and after of our before-after control impact study, to look at the sediment fluxes within the system. So we take a new DEM, or digital elevation model, an old DEM, and we get the difference. Based on that, we were able to show that there were, in some cases, almost 3 meters of scour, and in other cases, almost 3 meters of deposition. Being able to balance those in both the excavation area and in the swale, we estimate that there was a net production of over 300 cubic meters of sediment. Knowing this topography is also very important, and the type of sediments of that deposition is also very important to understand the groundwater response or the recharge to the local aquifer. So Graham Fogg and his students have constructed a regional groundwater model that's infused by information from sediment cores created during the creation of 12 monitoring wells distributed throughout the site that characterize the mud and the sand and the gravel and the composition of those along the study reach. And to be able to decompose that information into 3 dimensions and run groundwater models to look at the inundation pattern against these substrates at depth. Based on his work, looking at the 3.5-year floodplain inundation at different hours, we've been able to estimate that with this particular setback action and the increased frequency, about 3 times more frequently will be inundated than was previous with the constructed levees, that we're receiving about 100 to 300 acre-feet of recharge per event. So that's nearly 1,000 acre-feet of recharge just from this one simple action. The takeaways from this I had mentioned previously, but it does provide insights for us for the rest of the Central Valley. So how are these multiple benefits achieved, and what can we do with them? Oftentimes the Cosumnes is held out as the exception rather than the rule, in part because it has that natural flow regime and doesn't have a dam upstream. What can we do in other places that could benefit from what we've observed in the Cosumnes? To this we answer the use of functional flows. And functional flows aim to mimic the hydrograph, not fully, but at key points within the year. So high flows to mobilize gravels, perhaps attraction flows for different fishes, a snowmelt recession to better mimic the drawdown rate for cottonwoods and for frogs, base flows during the summer. That framework is newly published and is out, and is based on using these insights from natural systems to how we might improve the management of regulated systems. So where to from here? Well, I'd like to say that the Cosumnes is part of a puzzle. So if you look at the North Delta, where flood basins flank rivers, and that puzzle, which is the Cosumnes, it fits fairly neatly into some of the other things that we're trying to do, including the North Delta Arc and the work in the Yellow Bypass, and in particular the Najiri project at Nags Ranch. So those lessons learned: restoration, resilience, reconciliation. Multiple benefits are possible, but they require adaptive management and science-informed decision-making. In the end, the Cosumnes, being a black swan and its brown river, means that we can use an experimental system that is small enough to be manageable, but large enough to be meaningful. And with that, I'm going to say thank you to Treva Porter, one, for inviting me, but two, providing the oversight of this very kind of long and drawn-out set of projects that have provided us with the opportunity to bring insights to everyone else. Rod Kelsey at the Nature Conservancy and his colleagues, Judah, Sarah, Jamie Marty before she left TNC, Nat CV, and others that are part of the partnership. And of course the CRG3 crew and all the crews that came before them, and the administrative support we get at UC Davis. Thank you.
Thank you. So we have a microphone that will be passed around, so if there's anybody that has a question, we are on webcast right now, so if you have a question, we need to go ahead and use the microphone. So if there's anybody in the audience. If there's anybody on the WebEx that...
You know, Randy's here. He'll be able to assist. Maybe not.
He's going to get Randy, our IT guy.
I don't see any questions online.
Questions in the audience?
All right, with that, oh, sure.
Oh, great.
I'm John Anderson from Fish and Wildlife. I just have a curiosity question. At one time I was on a committee called the Cosumnes River Advisory Committee. It predated all of this, the preserve and all that. And one of the things that I noticed that the Cosumnes River Basin, you touched on it, but I'd like to know if it affects the regime and the overall restoration are the remnants of the hydraulic mining that took place along the basin, you know, the dredges and that sort of thing, and all those tailings and things.
Yeah, no, that's an excellent question, and I alluded to it a little bit in saying that the present channel is probably not where it used to be. And so there's been a wholesale change in the location and the nature of these channels. So where this particular study site is located is kind of right at that break point in terms of gradient. And up until recently had been a sand-dominated system. A lot of just sand deposition within the river itself and moving through, oftentimes, you know, knee-deep during summertime. And so it's long been thought that some hydraulic mining upriver created a sediment plug, if you will, that's been working its way through the system. There is some fairly persistent source of sand upriver. Right where Highway 99 kind of breaks the river is a place where the historical evidence, including the maps and these surveys, indicate that it probably was a distributary system right at that point. So it went from a single channel breaking into many channels and the remnant forest and into this Cosumnes sink, if you will. At some point in time, maybe in the 30s, based on the aerial photographs, we can see that a primary channel was formed into where it is today. And it's fairly clear that it's been incising through a terrace probably for the last 80 years, something like that. Now, there's no sand within that incised channel itself, but it's basically has been highly simplified, just kind of a U-shaped channel that is fairly flat, but with a lot of bedrock and a lot of sand moving through it. And in retrospect, thinking about how the levees kind of elevated the stream power in that case, we were moving a lot more suspended sediment through the system than perhaps we had realized. In part, I say that because now that we've alleviated that with the setback levee and access to the floodplain, there's a lot more gravel in there today than we had seen previously. And so presumably a lot of that was just getting flushed right through the system and we didn't know it. So there's probably a more heterogeneous mix of sediments upstream than just the sand, but there is a very large and persistent sand source somewhere up past Highway 16, presumably. I don't know if that answers your question exactly, but you know, the remnant effects of mining are still being felt throughout the Sierra Nevada. The Cosumnes is no exception.
Great. Yeah.
Yeah.
Hi, Kelly Barker with the department. I work with DWR and the Flood Board on the Central Valley Flood Protection Plan and its associated conservation strategy, which hopefully you guys are commenting on because it's almost out for public review. But they have identified a lot of ecological objectives in the flood system for reconnecting floodplain and hopefully for rock removal if we can get that through the Flood Board. My question is, did you have any issues with landowner liability concerns when you were reconnecting floodplain? Because we're running into that a lot with rock removal and with floodplain restoration.
Yeah, that's an excellent question. And my colleagues at the Nature Conservancy would be able to tell you hours worth of stories about the permitting process behind this particular research project. Prior to this restoration, the work in the accidental floodplain, if you will, and the triangle above it was really just, I mean, not that the Corps wasn't involved, not that the DFW wasn't involved. It was just more a guy with a dozer that popped a hole in the levees. This one, in part because of the nature of where it was, and in part because of the scale at which this was happening, required a lot more permitting and required fairly extensive modeling to show that, in fact, that there would be no net increase in the flooding risk to the adjacent landowners. Part of that, in addition to the modeling and just being able to show that, in fact, this was going to reduce flooding risk to the neighbors, is that a lot of the dirt that was removed from those other levees was used to reinforce levees between the property and the neighbor. So that was a bit of a win-win. That said, having to kind of jump through additional regulatory hoops, getting a stream bed alteration permit, getting a non-point source pollutant permit, some of the archeological aspects of it. The costs associated with this particular restoration are much higher than any of the prior ones. It'll be interesting to see whether the acres restored pencil out in a similar way, but certainly restoring the process has resulted in some benefits, even in this year where we only had one minor flood.
And then my other question was, you said that the framework for the functional flows is newly available.
That's right.
Where can we find that?
It's in bioscience. I'm happy to send you a copy. Sarah Yarnell, who's a senior scientist at the Center for Watershed Sciences, is the lead author. Chris Enright, in fact, is an author on that. So if you communicate with him, he can also provide you a copy. but it's in press. I think there's like a draft PDF, but I'd be happy to share it with you.
Okay. Thanks.
Anything else?
Okay. Is there any?
I was advised that it would actually pop up.
Okay, it would if there was anybody. Well,
All right.
doesn't look like there's anybody on webcast, so we thank you for coming and speaking. The department thanks you, and as well as the Resources Agency. Thank you very much.
Yeah. Thank you all.